Chapter 2.7, Nonlinear Inequalities. All right, in this section of the chapter, we are going to be talking mainly about polynomial inequalities and then rational inequalities and the steps for solving them. So, hopefully you recall solving linear inequalities from your earlier algebra classes. This is an example of a linear inequality. Notice that the degree or the power of the exponent, the highest power of x, is 1. Well, how do we solve linear inequalities? Just like we would solve a linear equation, we need to try to isolate the variable x. In this case, we would start off by subtracting 6 from both sides, giving us negative 3x is less than negative 18, and then we would divide both sides by negative 3. Now, hopefully you also recall that when you multiply or divide by a negative value in an inequality, you must flip the inequality sign, leaving us with x is greater than 6 for our final answer. As we said, don't forget to flip the inequality sign when multiplying or dividing by a negative. So what does our solution look like in interval notation? Well, we are going to be talking about values of x that are greater than 6. So we would have a parentheses 6 comma infinity with a parentheses. Again, hopefully you remember interval notation from earlier on in the year. We use parentheses if endpoints are not included in the solution set. 6 is not included in this solution set, but all values that are greater than 6 are included. All right, with infinity or negative infinity, it's always going to be parentheses. So what would our graph look like on a number line, our numerical number line solution? Well, we'd have to plot our value 6 on our number line, and we would put a parentheses at 6 and shade to the right. Okay, parentheses at 6 and shade to the right. Some of you guys in the past, you may have also used, instead of parentheses, maybe an open circle at 6. That's perfectly acceptable if you want to use open circles and closed circles. I just like using parentheses, and we'll use parentheses and brackets in this case because they match up with the interval notation. Notice if I have a parentheses at 6 in my interval notation, I should have a parentheses at 6 on my number line. So that's linear inequalities. Let's now talk about polynomial inequalities. Solving polynomial inequalities is a bit more involved, but we can make use of the fact that a polynomial can only change signs, meaning go from positive to negative or vice versa, at its zeros, right? If it's going to change from positive to negative, that means it has to go through 0. So what we are going to do is start off by finding the zeros of the polynomial. Then we can generate test intervals that will allow us to select particular values within each test interval to either confirm or deny as being solutions to the inequality. All right, here are your steps. Step number 1, this one's very important. Always start off by setting the inequality to 0 and making sure that it is written in polynomial form. Okay, oftentimes, right, with the highest power to lowest power, and make sure it is set to 0. 2, factor the polynomial and find all the real zeros of the polynomial. 3, arrange the zeros in order, increasing order, on a number line to create your test intervals, right? Put those zeros on a number line. 4, select an x value between and beyond each real zero to test in the inequality. We're literally going to plug that number into the inequality. If the test value generates a true statement, the inequality will be true for all values of x in that interval. If the test value generates a false statement, the inequality will be false for all values of x in that interval. And finally, 5, shade the regions or region of the number line that makes the inequality statement true. Add parentheses for endpoints that are not included in the solution set and brackets at endpoints that are included in the solution set. Again, if you wanted to, instead of parentheses, you could use an open circle, and instead of brackets, you could use a closed circle for those endpoints. All right, so let's give one a shot. Solve the inequality. Well, step number 1 is to set the inequality to 0 and make sure it's written in polynomial form. Notice over here on the left, this would be a quadratic, but it's currently factored. So to write it in polynomial form, we have to expand it. X minus 3 times x minus 3, that gives me x squared minus 6x plus 9 is greater than 1 in this case. So, as we also said, we want to set this to 0, so I subtract 1 from both sides of the equation, leaving me with x squared minus 6x plus 8 is greater than 0. So, we've written it in polynomial form, and we have set the inequality to 0. That was step number 1. Step number 2 is to factor the polynomial completely. X squared minus 6x plus 8. Well, what does that factor into? X minus 2 times x plus 4 is now greater than 0. Once we factor our polynomial, we can determine what the zeros are. Again, think about setting each one of these factors equal to 0. When does this equal 0? Well, the zeros are x equals 2 and x is equal to 4. Once I find those zeros, I am going to plot them on a number line. Obviously, 2 is less than 4, so 2 should be on the left of 4. This allows us to set up our test intervals. Notice we have a test interval for values of x from negative infinity to 2. We have a test interval of values of x from 2 to 4, and a test interval of values of x from 4 to infinity. We need to pick a value in each one of these test intervals and plug it into the inequality to see if it makes the inequality statement true. So, what's a number that's to the left of 2 that would be easiest to plug into the inequality? I would probably pick 0. So let's plug 0 into our inequality. Now, does it matter which one of these inequalities, these forms of the inequality that we plug it into? It does not. However, generally speaking, it is easiest to determine, all right, our whether or not it is a solution to the inequality by plugging it into the factored form. The reason is because we are testing to see if the polynomial is greater than 0 or less than 0, in this case greater than 0, it is only necessary to determine whether or not the polynomial is positive or negative at each test value. It is often easiest to do this using the factored form. In other words, I don't really need to know what the number is. I just need to know whether or not it is going to be positive or negative. All right, and using the factored form, well, notice if I plug in 0 for x, that leaves me with a negative number times a negative number. And a negative number times a negative number is always going to be a positive number, and a positive number is always going to be greater than 0. This is a true statement. All right, so I put a little check mark above that interval. Notice at the end, we're going to have to shade that interval in. Next, let's choose a test value between 2 and 4. What's an easy number between 2 and 4 to plug in? Well, I would probably plug in 3. Again, plug it into the factored form and simply analyze the sign of each of the factors. All right, is it positive or is it negative? If we plug in 3, this first factor is positive, the second factor would become negative. A positive times a negative. Is a positive times a negative going to be greater than 0? No, a positive times a negative is always negative. Therefore, that is a false statement, meaning my inequality would not be true. So let's put a little x on that interval. We're not going to want to shade in that region. And finally, let's choose a test value that's to the right of 4. What's a really easy number to plug into the right of 4? 5. And again, you could pick any number to the right of 4 that you wanted to. You could pick 100 if you wanted to. All right, 5 is probably pretty easy. So if we test 5 into our factored form, that gives us a positive value times a positive value. And is a positive times a positive going to be greater than 0? Yes, that would give us a true statement. So we put a little check mark up above that region. Now we just need to figure out where to shade. Anywhere that we have a check mark, we are going to shade. So we would shade this region from negative infinity to 2 and the region from 4 to infinity. We must also decide what to put at each one of these endpoints. Well, is 2 a solution to the inequality? No, plugging in 2 would make it equal 0, and 0 is not greater than 0. And because this endpoint is not included, we would put a parentheses here. Same thing with 4. 4 is not a solution, therefore we put parentheses. And notice the direction of the parentheses. They should always go towards the direction you are shading. All right, and so there is our answer graphically on a number line. What would our answer be in interval notation? Well, over what values of x do we have solutions? From negative infinity to 2 and from 4 to infinity. Therefore, our solution in interval notation is parentheses negative infinity 2 with parentheses, union 4, comma, infinity, both of those with parentheses as well. Again, make note that the parentheses are used because they are not solutions. They are not included in our solution set. Let's try another one here. Solve the inequality. We have 4x squared minus x to the fourth is less than or equal to 0. Okay, so the nice part about this inequality, it's already written in polynomial form, okay, and it is already set to 0. So the next step is to factor. And whenever we go to factor a polynomial, we should always look for a greatest common factor first. Notice in this case, we can factor out an x squared. This leaves me with x squared times 4 minus x squared. And we can actually continue to factor this, right? 4 minus x squared, that's the difference of squares. That leaves me with x times x, right? That's my x squared, times 2 plus x times 2 minus x is less than 0. There is the completely factored form of our polynomial. And once we have our factored form, we can identify the zeros. What makes this equal 0? Well, set each of the factors equal to 0. We get x equals 0, x equals negative 2, and x is equal to positive 2. Once we find the zeros, we want to plot them on a number line. Okay, we have negative 2, 0, and positive 2. This allows us to set up our test intervals. I need to test a number that's between negative infinity and negative 2, test a number that's between negative 2 and 0, test a number that's between 0 and 2, and test a number that is between 2 and infinity. All right, so what's a number that is to the left of negative 2 that would be easy to test? How about negative 3? Well, let's plug it into the factored form. Again, remember, it's always easiest to plug into the factored form and analyze the signs. If I plug in negative 3 for x, I get a negative times a negative times a negative times a positive. What's a negative times a negative times a negative times a positive? Well, a negative times a negative is a positive, times another negative gives us a negative, times a positive is still negative. Is a negative number going to be less than or equal to 0? Yes, that is a true statement. All right, so we put a little check mark up above that region. Now let's choose a test number between negative 2 and 0. How about negative 1? If we plug in negative 1 for x, that gives me a negative times a negative times a positive times a positive. Well, a negative times a negative is a positive times a positive times a positive gives me another positive value. Is a positive number going to be less than or equal to 0? No, that gives me a false statement. Therefore, I'll put a little x over that region, telling me not to shade there. All right, now let's choose a test point between 0 and 2. Let's test 1. If I plug in 1, I get a positive times a positive times a positive times a positive. Well, that's definitely going to give me a positive, which means I have a false statement. A positive value is not going to be less than or equal to 0. So I put another x on that interval. And finally, I need to choose a test value that's to the right of 2. Let's test x equals 3. If I plug in 3 for x, that gives me positive times a positive times a positive times a negative. Well, if I were to multiply all those out, I'd get a negative number. Is a negative number less than or equal to 0? Yes, that is a true statement. Therefore, I'll put a little check mark up above. So, where do we want to shade on our graph? Well, we definitely want to shade the regions where we have check marks. So from negative infinity to negative 2, and from 2 to positive infinity. Now at negative 2, I am going to put a bracket. Why am I going to put a bracket at negative 2? All right, well, that is a solution to the inequality. Notice that in this case, all the zeros are included as solutions. So I'm going to have a bracket here on negative 2. Because the zeros are included as solutions, right? Plugging in 0 gives me 0 is less than or equal to 0. I actually also have a filled in circle here at 0, and then also a bracket at 2. All right, so each one of these zeros that we found is included in the solution set. All right, now the reason we use a filled in circle here is just because it's a singular value, okay? We would not be able to use brackets for some type of interval. So because it's a singular point, a single value of x that is a solution, we're just going to use a filled in dot. So there's our graphical answer. What about our answer using interval notation? Oh, real quick, brackets are used instead of parentheses since the endpoints are included in the solution set. A solid dot can be used to represent a singular solution point. And so what's our answer going to look like in interval notation? Well, again, we always want to go from left to right, our lesser numbers to our greater numbers. This gives us negative infinity, comma, negative 2 with a bracket, in union with 0 on its own, that's its own value, in union with bracket 2, comma, infinity. Again, notice the brackets mean that those values are included. And there you have it, solving polynomial inequalities.